Hello, this is Mr. Koulis. We are going to do some extension problems over composite figures, which was chapter 10.3. You've already watched the video and done a little bit of homework over that. We're going to do some harder problems, some ones that trip kids up. Take really good notes here, and you'll have an opportunity to use those for a grade here. So let's get after it. A composite figure is just a figure made up of a bunch of other figures. For instance, in this, I see a circle or half of a circle here. I see a square, maybe a rectangle. Looks like I have a 10, and across the rectangle it looks like it's 8. So I guess that's a rectangle, not a square. And then I see a triangle. And the overriding concept of a composite figure is that you're going to divide it up into pieces that you know. And then after you do that, you can find the perimeter or find the area. So I have my calculator here. We're going to go through, we're going to find both the perimeter and the area. And the perimeter is still find the lengths of all the outside edges and add them up. And the area, we're going to divide it up into pieces that we know. And then we'll be able to find the area by adding up those values. So I'm going to put P equals, and I'm going to go through and I'm going to find my perimeter first. So here we go. I got a 10. I got some value I don't know yet, another value I don't know yet. I have a couple tick marks there. Well, if I divide it straight down, I notice I have a rectangle right there. So if that's 10, I can put a 10 here, and I probably really, honestly, I should have right angles in there. I'm going to assume it's a rectangle. It looks very rectangular. Put a 10 there, and I'm going to put a 10 there. So I have 10, I have another 10, and I have another 10. So far I have 3 10s. So 10, another 10. And then I need these pieces, which a little bit tougher. But I notice here, I got this dotted length here. That would be 8 because it's 8 across the circle. That's what that bracket there is showing me. So that tells me this is 8. And I'm not going to use 8 for the perimeter because it's on the inside. But that makes this 18. And I also notice I have a 45, 45, 90 triangle. And a 45, 45, 90 triangle, the two legs are the same. So I know if that's 18, I know that is going to be 18. So I have another 18. And then in a 45, 45, 90 right triangle, it goes x, x, x radical 2. So if this is my x value, this is my x radical 2 value. And if x is 18, then this side over here is 18 radical 2 right there. Plus 18 radical 2. And then all I got to do is add on this curvy part. And the curvy part there is half of a circle. Now we are doing perimeter, so this perimeter would be the circumference formula. It would be half of the circumference formula. So I'm going to put C equals 2 pi r, and then what I'm going to end up doing is I'm going to multiply that by a half. And one thing you notice there's a 2 and there's a half. Those two things will cancel each other out, and I'll be left with pi times the radius. The half and the 2 wipe each other out. My radius, well, my diameter is 8. I can see that, so my radius right here is 4. So I'll put a 4, and it's pi times 4, which we know we can write as 4 pi. Now, that's a big long thing, and you could decimalize that pretty easy. You could add all these values up, and you could hit equals, and it would tell you the decimal. Or I can add up the parts that go together and leave it in an irrational form, which is what the ACT will show you. So 10, 20, 30, 48 plus 18 radical 2 plus 4 pi. And if you're on the ACT and it asks for the perimeter of this figure, that's what it would tell you. And go ahead right now, as part of your notes, I want you to also go ahead and run through the decimal approximation and put that right down there also. You can pause the video and finish that up. Okay, part 2. Part 2 is find the area of this figure. I'll do this in blue. Well, I've already have it divided up. That's kind of nice. I have a triangle here, I have a rectangle here, and I have half of a circle. And I did already use that 4 pi, found that value right there. I'll highlight that. And this is not too bad. So sometimes what I'll do if I have enough room is I'll go right inside the figure so I know I've done it. So here I have area of this triangular region is 1/2 base times height. I take 1/2, the base is 18, and the height is also 18. And just to make sure I get it right, I think it's half of 324 is 18 times 18. But I'm going to go ahead and use a calculator. 1/2 of 18 times 18. I got 162 for this region. For this rectangular region, my area is base times height, and my base is 10 and my height is 8. So I'll take 10 times 8. I don't need a half, but that's 80. And then for this half of a circle, I'll say area is equal to pi r squared. And again, I need half of that. I don't want the whole thing. Just want half of the circle. So I'm actually, go ahead and I'm modifying a formula right now. And if I had like a little pi piece that was 1/4 of the circle, I'd multiply by 1/4. So sometimes you're going to have to take these formulas and just modify them out. So I'll leave the half there, but again, my radius was 4. So it's pi times 4 squared times 1/2. I can't take half of 4 now. I have to square it first. So I'm going to square 4, and I get 16. And half of 16 is 8. So it's 8 pi square units. This part is 8 pi square units. So if I was going to add these together, I would take 162. I would add to it 80. And 162 plus 80, I just did on my calculator, is 242. And then I'm going to add to it the 8 pi region, and that would be units squared. And go ahead again and find your decimal approximation for that. Just use your calculator. Go ahead and include that as part of your notes right there and circle it. Okay? That's problem number 1. That's a composite figure. Part number 2, I call the whole problem. And there's a lot of times in geometry, I see this problem on the ACT, SAT about every other time. I mean, there's some form of this problem just all over. There's a hole cut out of something. So I have this figure around the outside, and in this one it's a hexagon. This actually looks like a hex nut that you would put on a bolt. Maybe use your wrench, you turn it on there. It's got grooves on the inside. Whatever. This happens to be a hexagon and a circle with it's kind of like a donut problem. You have the hole cut out of the middle. And what do you do? So the overriding formula for hole problems, when I have a hole in it, is I'm going to take whatever's around the outside, I call it the outer, and I'm going to subtract off whatever's on the inside, the inner. And that's the basic formula for a hole, if you're going to subtract it. And it doesn't matter what it is. In this case, it would be hexagon. I'd take the area of the hexagon, and I would subtract out the area of the circle. But, I mean, that's just for that one. I mean, if it was like, here is a square, and here is a triangle, and it wanted you to find the area of the shaded region, you would do square minus triangle. And even sometimes maybe we'll have a, I don't know, maybe we have a circle, and then we have a square, and a half of a circle, and then we have, I don't know, maybe we have a pentagon in here. That would actually be a really hard problem. And then maybe it has this shaded area, and I'm just totally making this up. But I mean, what would be what would we do on that? What do you think the formula is? Well, we go circle minus, and then I would want to parenthesize, so I subtract them all off, and I would go minus the square, minus the half of a circle, and minus the pentagon. And I could find the area of the shaded region. But that's the idea of the whole problem, is whatever you have around the outside, you're subtracting off whatever's underneath. Okay? Time for the move of the day. Here we go. Are you ready? All right, get your body moving, it's important. All right, back to the whole problem. All right, so now we have a problem that says find the amount of red in the picture. And this is really one of my harder problems, one of my big ones, one of the ones that tell me, hey, are you getting geometry just in general? And we see this again in Algebra 2, and we see this again in pre-calculus. So this is like, you're going to see this problem again and again, so it's going to be important. So it says find the amount of red in the picture. My outer this time is a circle, and my inner is a hexagon. So just if I use the formula outer minus inner, it's going to be circle minus the inner is a hexagon. Circle minus hexagon is what I'm looking for. Okay? The hard part is it didn't give us any measurements, but it gave us the perimeter of the hexagon, and we would have to assume this is a regular hexagon. All the sides, all the angles are exactly the same. But it tells us the perimeter of the hexagon is 174, and I'm going to have to use that to go in and really get me some links on this picture and go from there. So I'm going to do the hexagon. Let's do it in blue here. I got blue. Regular hexagon perimeter is 174. So if I take 174 and divide it by 6, I just found 29. Okay, and that 29 value, that's going to be the length of a side. So I'm going to just bracket it off from there to there. I'm going to put a 29 right there. And just like before, we're gonna take this thing, and there's not a lot of change in what we're gonna do. We're gonna divide this thing up into triangles. And there's 6 triangles. And if I could just find the area of one of those triangles, I would know what the area of the hexagon is by multiplying it by 6. So I got the base is 29. I'm gonna have to find the height of the triangle right there. I'll call that the h value. So I got the base 29, I got the height. Oh, I got to go in and I got to find that angle right there. And that angle has a formula. We take n minus 2 times 180 and we divide it by n. And your n is your number of sides. So I want you to pause the video. I want you to go in and I want you to find that angle. Okay, so I plug in a 6. 6 minus 2 times 180 divided by 6. You should have gotten, out of all of that formula, you should have gotten 120 degrees right there. So I know this whole angle here, that whole thing is 120, which means this little slice over here that I'm going to use in my trig is 60 degrees. So I have a little 60-degree angle right down in there. And I'm going to use that to find the radius of the circle and the height of the triangle and all of the jazz that goes with that. So I got a 60, I got a 29. Ooh. I need half of that 29 to use in my calculations, and I'm not going to use all of 29. So half of 30 is 15, so half of 29 is going to be 14.5. So I'll put a 14.5 right down there. And really what I need is I need that height, and for the circle, because I got to find the area of the circle also, I'm going to need to find the r. So I need to do trig formula, trig calculations to go ahead and find the h and r. And again, I'd really like you to press pause. I know it's easy to fast forward through videos and see what I've already done, but to get this, I'd really like you to press pause and see if you can find both the h and the r right now with that 60-degree angle and that 14.5. Okay, back at it. 60, I got h is opposite. I got 14.5 is adjacent. So opposite, adjacent. Ooh, I should write it up. So ka toa. All right, so I got opposite, adjacent. Opposite, adjacent. Opposite, adjacent is tangent. So I'm going to write the tangent of 60 is equal to opposite, which is h, over adjacent, which is 14.5. I'll put the tangent of 60 over 1, and I'm going. So here we go. Let's take it. The tangent of 60, when I cross multiply, I'm going to multiply that by 14.5. See, what I did was I did 1 times h tangent of 60 times 14.5, and that's going to give me my h value. And I got an h value of 25.1. Okay? Now I'm going to go and I'm going to find the radius of the circle. So this right here, 25.1. And now I'm going to go and I'm going to find the r. Definitely have some ways to do this. I could use Pythagorean theorem, leg squared plus leg squared equals r squared. I'm probably just going to use SOHCAHTOA with the 14.5 and the r. So that's adjacent and hypotenuse. Adjacent, hypotenuse, adjacent, hypotenuse. That's cosine. So now I'm going to crank through the cosine of 60 is equal to adjacent 14.5 over hypotenuse r. And this one's set up a little bit differently. When I cross multiply, I'm going to have to divide. So I take the cosine of 60 times the r value is equal to 14.5. I'll divide by the cosine of 60. And I end up with an r value that's 14.5 divided by the cosine of 60. And I'm hoping that you have a calculator out also. Bang, you got 29 is what I got right there on my calculator. You can hit pause, make sure your calculator looks the same. Which kind of makes sense. It is a equilateral triangle. This is 29. If that angle's 60, it goes 29, 29, 29. So it's not really all that surprising from a geometric standpoint that I got 29. I'm going to switch colors. This blue's running out of ink. So here we go. So I got my radius is 29. I think I have everything I need. I'm going to go in and I'm going to finish off the problem. So first of all, the circle, the circle. The circle is pi r squared, which is pi, and my radius is 29. So 29 squared. I'm going to go ahead and I'm just going to crank this out. I'm going to go ahead and decimalize this one. So I'm going to take 29 squared times pi. And I got 2642.1. 2642.1. And then I'm going to subtract off of it the area of the hexagon. And to find the area of the hexagon, I'm going to find the area of one triangle. And I'm going to multiply it by n, the number of sides. So if I find the area of this guy, I have 1, 2, 3, 4, 5, 6 of those triangles. I'll find the area of that one and I'll multiply it by 6. So one of the triangles is 1/2 the base times the height times n. Let's see if we can plug numbers in. So I take 1/2 the base, 29, the height, 25.1, and n, there's 1, 2, 3, 4, 5, 6 sides. And again, I'm gonna, because this is a decimal, I'm just decimalizing it all. But I'm gonna go through and I'm gonna find that number. So I got 0.5 times 29 times 25.1 times 6. And I got 2183.7. 2183.7, and here I got 2642.1. And I look at those numbers and I like looking at them and I like to say, okay, is that reasonable? So my circle is about 2600 and my hexagon is about 2100, and it makes sense to me because look, the hexagon almost fills up all of the circle. I mean, it's filling up a lot. There's not much red there. So it would make sense to me that the circle would have a little bit more area than the hexagon, because the hexagon is actually inside of the circle, taking up a lot of its space. So these two numbers, they make sense to me. So now I'm going to take those two numbers and I'm going to subtract them. take that, and I'm using my calculator version, so more of an exacting value. I'm going to subtract off that. And I got 458.4. I got an area of red. Area of red is equal to 458.4. I think that was right. 458.4. 458.4. And let's see, do we have a label? We have inches, so that would be inches squared. And I found the amount of red in the picture. And that is it. That's one of the harder problems that we do. The reason I like it so much is because I see a formula here from a chapter, trig stuff from another chapter. It uses, you have to know what regular means. You have areas of circles, areas of hexagons. You have outer minus inner. This problem really encompasses so much of what we talk about in geometry. It's like half of the class rolled up into one problem. So good job today, and have a great rest of your day.